More about differential equations. So turn with me to page 413. In the preceding section, you learned to analyze visually the solutions of differential equations using slope fields, and we didn't approximate solutions with Euler's method. It's not part of our curriculum. Analytically, you have learned to solve only two types of differential equations. The derivative equals f of x, and the second derivative equals f of x. That seems like a lot, and it is, but we're going to do more. In this section, you will learn how to solve a more general type of differential equation. The strategy is to rewrite the equation so that each variable occurs on only one side of the equation. This strategy is called separation of variables. It's called separation of variables because you separate the variables. You put the y's and the dy on one side, you put the x and the dx on the other side, or maybe it's t's and dt's, okay, whatever the independent variable is. Okay? Now, here's a note. When you integrate both sides of the equation in example 1, so if you look at example 1 in the book, the differential equation is y prime equals 2x over y. It says when you do this, you don't need to add a constant of integration to both sides of the equation. If you did, you would obtain the same result. It's kind of like when we take the integrals, you know, if we have 2 or 3 different integrals because we've separated it up, we don't have to put a plus c every time because all we're going to do is add those c's together at the end anyway. If you have a c on the left and a c on the right, you're eventually going to subtract one from the other to get a new c. So why bother? Just put a c at the end. Okay? On the right side. Yep, on the right side. In practice, most people prefer to use Leibniz notation and differentials when applying separation of variables. The solution of example 1 is shown below using this notation. This is the notation we're going to use. So let's walk through this. So we've got the derivative equals 2x over y. They started with y prime. Change the y prime to dy dx equals 2x over y. Now, the separation of variables step could be steps sometimes. It's algebra, okay? So what they've done here is they've multiplied both sides by y so that that happens, and they've multiplied both sides by dx so that that happens. So what you're left with on the left side is y dy. What you have on the right side is 2x dx. Everybody follow me? And that's a fairly simple example of separation of variables. Okay? And it comes up quite a bit. Not only is it simple, it comes up quite a bit. All right? So we've got the y's and the dy's on the left, the x's and the dx on the right. Integrate both sides. So that's what they're doing on that step. On the left side, well, the integral of y, use the power rule on it. Add 1 to the exponent. Now it's a 2. Divide the coefficient by that new exponent, so that makes it a 1/2. So 1/2 y squared. Don't bother putting c. Equals, on the other side, the antiderivative of 2x. Power rule that one. Add 1 to the exponent. Now it's an x squared. Divide your coefficient by that new exponent. 2 divided by 2 is 1. So it's just x squared. Now, go ahead and put a plus c. And they put a plus c1 because they knew that they were going to multiply both sides by 2 to get rid of that fraction. So you get y squared equals 2x squared plus, and you don't want to write 2c1, just call it a different c. And then they went and got c by itself. There's lots of different ways we can end our answer. Okay? If it's convenient, you solve it for y. But that one's really not ruled convenient because then you'd have a square root and you'd have a c under your square root, and it's kind of nasty looking. So I would be okay with that. We really need to strive for that. That's fairly common practice. If you don't solve it for y, sometimes then you get it so that the c's by itself. And there will be others where we just, we leave it more like what I have the check mark next to. Okay? I doubt it. He asked if you don't call that one C1 and that one C, if you don't make them different, will they count off? I don't recall that coming up and being an issue, so I guess I'd say I doubt it, but try to remember to do it. Let's put it this way. If I was Mr. AP, I would, because you're supposed to get them right, So, but I don't really think they do, but I'm not sure. And a lot of it depends, too, as I've discovered over the years. It kind of depends on how many, every one of the free response questions is worth 9 points. So if it's a problem where they have to kind of stretch it to get that 9th point, it's more likely to matter. If it's one where it could have been 1,000 points and they just kind of narrow it down, then it won't matter. And how do you know which that is? Yeah. Just throw it on the right. Put it on the right. All right. Growth and decay models. And we've actually used this previously without knowing where it came from. In many applications, the rate of change of a variable y, rate of change of y, derivative of y, is proportional to the value of y. If y is a function of time, t, the proportion can be written as shown. The rate of change of y, the derivative of y, if t is the variable dy dt, all right, is proportional to the value of y. So equals some constant times y. The general solution of this differential equation is given in the following theorem. And I will show you how we get this in just a moment. But let's look at their theorem first. It says if y is a differentiable function of t such that y is greater than 0, and I really wish they hadn't written y prime. I wish they'd have written dy dt equals a constant times y for some constant k, then y equals c e to the kt. Remember using that one day? Just all of a sudden they had some problems where they gave us that we filled in some stuff. It was in the same time we did that PERT, a equals p e to the rt. It was the same time. C is the initial value of y. All right, you've got to know that. C is the initial value of y. K is the proportionality constant. Exponential growth occurs when k is positive. Exponential decay occurs when k is negative. So that's why it's growth and decay. Now, decay sounds kind of gross. It doesn't necessarily mean that. It just means that instead of getting larger, whatever you're measuring is getting smaller. Okay? It doesn't actually necessarily mean that it's rotting. All right? So growth means whatever you're measuring is getting larger. Decay means whatever you're measuring is getting smaller. All right? Now, let me show you where this came from. If y equals c to the kt is a function of time because t is the variable. C is a constant and k is a constant. Now, we'll use the given information to find them. Okay? They'll tell us, sometimes they'll just flat out tell you, well, then it's a plug and chug problem. So how often do you think that's going to happen? Yeah, one example maybe, and then we'll move on. So they'll give us some information. We'll have to figure out what C equals and what K equals. Okay? Then we'll answer the questions they ask us about our function. Now, here's how they came up with y equals c e to the kt. And I think this is worth looking at. Here's our differential equation. Dy dt equals k times y. All right? Separate the variables. So multiply both sides by dt so that you can do that on the left. And then multiply both sides by 1 over y so that you can do that on the right. So you're left with 1 over y dy on the left, and you're left with k dt on the right. You following me? Y is your function. Okay? Now, hang on. Let me do something else here. All right, now that I've changed the battery. Integrate both sides. So you've got the integral of 1 over y dy on the left. You've got the integral of k dt on the right. All right, the integral of 1 over u du is the natural log of the absolute value of u. So the integral of 1 over y dy is the natural log of the absolute value of y. Now, k is a constant. So the antiderivative of a constant is that constant times x. Or in this case, that constant times t. Okay? So kt plus c1. So far, so good? All right, now, we exponentiate both sides to get rid of that natural log so that we can try to solve this for y. Because like I told you, if it's convenient, we'll solve it for y. Meaning, if we can do it and then the answer isn't just horrible, we'll solve it for y. So we e both sides. On the left side, e and natural log are inverse functions, so we get y. And we don't need the absolute value signs anymore, and to be honest, I don't remember why. Oh, because you can't e it unless that's a positive? Is that right? That must be it. Okay? Now, look what I'm doing on the left. You know that when you multiply factors with the same base, you add the exponents? We've got two things added together in our exponent. So use that property backwards to turn that into e to the first part times e to the second part. See what I did? Now, e to the some constant is itself a constant, isn't it? Because it's a constant to a constant, it's a constant. So call that c and put it in front. And that's how you get y equals c e to the kt. Okay? And I really do think that's worth knowing. Now let's do some examples. So I'm now on page 418. Let's take a look at number 4. Solve the differential equation. So we have dy dx equals 4 minus y. We need to separate the variables. If I multiply both sides, let's see, let me move that over a little bit. If I multiply both sides by dx, then, no, I didn't write that right, did I? By dx. Then I can do that on the left, and I only have a dy on the left. But look what happens on the right. Now I've got an expression with y on the same side as the dx. How do I get rid of that 4 minus y? Multiply by, how about 1 over 4 minus y? That way, I get to do that. So I have 1 over 4 minus y dy equals dx. Okay, everybody with me? All right, take the integral of each side. So that would be the integral of 1 over 4 minus y dy equals the integral of dx. And that looks a whole lot like the integral of 1 over u, doesn't it? but we got to make the du work out. So what should u equal? Let u equal 4 minus y. What's du equal? Du equals negative dy. All right, so if du equals negative dy, we know that then negative du equals dy. Do I need a substitution on the other side? No, I'm good. All right, so let's rewrite then. So replace the 4 minus y with u. Replace dy with negative du. And we're good on each side now, aren't we? So on the left side, we have the negative in front. Then the integral of 1 over u du is the natural log of the absolute value of u. Don't bother with the plus c yet. On the other side, the integral of, that's a 1 dx, isn't it? So what's the antiderivative of 1? X. Now put the plus c. So x plus c1. All right. I don't like that negative sign over there with what's eventually going to be my y. Oh, go ahead and put the 4 minus y back in. I don't like the negative sign over there with what is now my y. So how about if I just multiply both sides by negative 1? Now, you know when we were developing the y equals c e to the kt, we exponentiated both sides to get rid of the, so that the y wasn't trapped inside that natural log anymore. Same thing. Exponentiate both sides. And on the left side, e and natural log are inverse functions. So e to the natural log of 4 minus y is just 4 minus y. And then on the right side, I'm using that property backwards again, that when you multiply two factors with the same base, you add the exponents. I've got a base of e, and I've got two exponents added together, a negative x and a negative c1. So rewrite that as e to the first one times e to the second one. So e to the negative x times e to the negative c1. Now, e is a constant, c1 is a constant, therefore negative c1 is a constant. So a constant to a constant is a constant. So I'm now calling that c. So I've got 4 minus y equals c e to the negative x. And I can solve this one for y. Let's subtract 4. Should have kept the negative where I had it to start with, because now it would just multiply by it. So multiply both sides by negative 1. And there we are. Questions on number 4? Number 5. Solve the differential equation again. Y prime equals 5x over y. All right, y prime's no good. What's better? Call that dy dx equals 5x over y. And finish this one on your own. Separate the variables, then integrate both sides. In this one, I didn't actually solve for y. I got y squared equals is where I stopped. So separate the variables, integrate both sides. Separate the variables, integrate both sides. I don't know for sure because I haven't looked. I'll bet the book has that as the answer. But obviously, I'm okay there since that's where I stopped. Were you able to do number 5? Okay. Any questions yet? All right, let's do number 15. All right, they've given us, we've done tons of questions like this one. The difference now is we know how to separate the variables, which really we've done before. We've started with dy dx, and then we've said we'll multiply both sides by dx. But there's a little more to it than just multiplying both sides by dx on this one. But we've got the slope field. The first thing they want us to do is to sketch 2 approximate solutions of the differential equation on the slope field. So you can see what I got. I started here, kind of does that, kind of does that. Oops, well, kind of. And ooh, just to make it different, what would happen if I started up here? It'd be no, because then it's, man, what is that doing? I don't know, it's kind of tough. Should have stuck with what I had, shouldn't I? Okay, so you got your sketch, and that's all it is a sketch. Now, the part we need to concentrate on. Use integration to find the particular solution of the differential equation. So before we can find the particular solution, we find the general solution, which is what we've been doing. So let's take a look right here. Oops, looks like I've skipped a little bit. So we start with dy dx equals x times the quantity 6 minus y, and then our particular solution will be at the point 0, 0 here in just a minute. But how do I separate the variables here? I need to do 2 things. I need to multiply both sides by dx, and what else do I need to do? Multiply both sides by 1 over 6 minus y. All right, so on the left side, the dx is divided out, leaving me with 1 over 6 minus y dy. On the right side, it's the 6 minus y's that divide out, leaving me with x dx. So I've separated the variables, then I integrate both sides, and that gets me here. All right, you guys with me? The left side looks like a 1 over u. So what are we going to let u equal? All right, this is about to get old. So let u equal 6 minus y. Then du will be negative dy, which means negative du is dy. So we can do our substitution. Make that the integral of, and then replace the 6 minus y with u, and then replace the dy with a negative out in front of the integral, du, like so. Now let's do the integration on both sides. Oh, actually I multiplied both sides by a negative. Yeah, I don't know. Maybe I kind of regretted it last time. Let's see if I like it or not. So I don't care if you do or not. We'll see. All right, what's the integral of 1 over u du? Yeah, maybe you've got a negative in front of it. Maybe you don't. Depends on where you put your negative. Natural log, absolute value of u. All right, and I've got my negative on the other side, so the integral of x will be negative 1/2 x squared, because I've got the negative there, plus a constant. Now, let's go ahead and replace u with what it equals. And let's exponentiate both sides. We are so talented we can do two things at once. Replace u with what it equals and exponentiate both sides. What do you get on the left? 6 minus y. And on the right, we've got e to the, and then our exponent is two things added together. So go ahead and use your property. Make it e to the first part of your exponent times e to the second part of your exponent. If you had the negative on the other side, it'd be a positive y and a negative 6. All right, so e to some constant is in fact a constant. And I subtracted 6 from both sides. So yeah, I kind of regretted it this time again, didn't I? I should have just left the negative on the left and it would have taken care of itself. But now I've taken care of it. Now, when I do, technically speaking, this constant that was right here just got multiplied by a negative 1, so it's a new one, technically. Okay? All right, so we've all got it solved for y. You with me? Yes.
When I put the negative on this side, I got positive. Oh, yeah.
That's okay because you've got a different constant than I have.
Okay.
Let's watch what happens. Because now that's our general solution. Our particular solution is at the point 0, 0. What do you put in for x? 0. What do you put in for y? So those of you that had your negative in a different spot, did you get a positive 6 for C instead of a negative 6? No? You still end up with a negative 6? All right. So does that now mean that we all get this? Or do you still not have, we still not have the same thing? Still got the positive 1/2? They must be equivalent. Because you left your negative, where did I get rid of my negative?
Way up there. The one.
All right, so you would have had, let's see. So starting here, so you would have had a negative there, and that wouldn't be there. So then you'd have a negative there. That wouldn't be there. So then, you know what? I think we've got to get rid of it here. I don't think that makes any sense. If we leave it there, I've got 6 minus y. I've got to then do the natural log of the
Do not.
the natural log of the absolute value of 6 minus y to the negative 1. Make that e to the natural log of 1 over 6 minus y. Yeah. So I no longer regret my multiplying both sides by negative 1 because it didn't work out quite as nice as I thought. And that's my fault. I told you it would. I was wrong, wasn't I? Ooh. I just said that and it got recorded too. All right, somebody's got to help me later learn how to edit this thing, okay? Because I don't want the whole world to know I just admitted to being wrong. But I was wrong. So I really do go ahead and get rid of that negative for these cases. Yeah.
Not negative, so it should be negative 1 and
No, you've got to. I mean, you mean way back up here? Where did you mean?
it's like the step right below what you just circled.
Okay. I mean, you can make that the natural log of that. Do what now? No, because that, I can't distribute that through there. Our property says that that can become an exponent of it. So, let's all learn the lesson. Put the negative on the other side. Yeah. Mm-hmm. All right, so fix yours. If I led you astray. So it is going to be better. You're all going to be better off having any negatives on the right side for just such cases. And now, for the moment you've all been waiting for. Page 418, 1 through 19 odd, 25, and 27.